Hi, Radu.
Hello?
Can you hear me?
Yes, I can hear you. Can you hear me?
Yes.
Great. Yeah. Okay. So I had to reset the laptop. That was the problem. Okay. So I have a super basic question. So when we play these videos, do we play locally on our computer or we click on some link here on the website?
I think everyone will do it on their
Locally, right?
Yeah, locally, yeah.
Well, hopefully the link and everything will go well, meaning I'm connected through the Ethernet actually. Let me double check. Because I hope, yeah, I'm connected through the Ethernet, so the link should be stable. But just in case something goes wrong, this is the issue, right? Okay, so I'm going to do a quick test then. Share computer sound, share screen, share, okay.
We can see your desktop.
Yeah, so let me see if I can go. Yeah, I reset it, so all the folders are closed now. Good afternoon and welcome to our tutorial on Edge AI. This is a joint presentation by Radu Marculescu, Diana Marculescu, and Umit Ogras. Umit, can you hear With the explosion of big data, it is often forgotten that much of the data... What?
Yes, I can hear it.
It's good quality because for some reason my volume is at maximum. I don't know why. This one, you see it?
Good. Yeah, quality was very good.
Okay. Yeah, let's do... Nowadays is generated at the edge. Specifically, a major source of data comes from users' endpoint devices, such as smartphones and watches that are connected. So Yebo, can you hear me?
He is muted. Yebo, you are muted.
Oh, I see.
Yeah, I think everything looks good.
So Umit, also have your phone ready just in case we need direct messaging.
Okay.
Yeah, so yeah, I added all this information on whatever is the name of this. I don't even know how to pronounce this. This thing. You see, I put the structure of the tutorial. I put everything here on online. But yeah, so I think the only thing I need to do now, Umit, is to make you co-host. I forgot how to do that.
Under more, there's a menu. If you click
where I see you, right?
yeah.
Make co-host. Okay. And that's your co-host now. Do you see that?
It doesn't show me, but yeah, probably I am.
Actually, good point. How do I know? No,
In
you are co-host for sure. Because when I look, it appears withdraw the co-host permission. So you are co-host now.
Okay.
The only thing is, yeah, so when Diana connects, I should make her co-host too. Okay.
Hi, can you hear me?
Yes. Can you hear me?
Yeah, just joined.
Yeah. So, yeah, okay. So I'll let a little bit the slides play. Umit confirmed me already. He hears very well. I want to make sure you confirm. Okay, so I'll start it now.
Okay.
connected to the internet, also known as Internet of Things. This edge of data faces several new challenges related. Is good?
Yeah, it's very clear to me.
Okay, good. I wanted just to test this. So basically, we'll monitor this chat thing because, I mean, these things can easily get out of control if the questions come like an avalanche. So I'm trying to see how can I see this this chat and these participants at the same time. I don't know how to do it.
I see it by default. I can see both the chat, participants, and the video.
Yeah, well, probably.
Can you just show the screen of the player instead of the whole screen?
So what should I do?
Currently, you are sharing the whole screen of your computer. You can simply just share the screen of the player so that you can see the player and the Zoom.
Oh, okay. Let's see. Stop sharing. So, okay. So you said I should share
only the player screen.
Or in the player. Okay. Yeah. And then, but I still don't have the chat. I cannot see the chat. I don't even have the option to see the chat. If you know what I mean. Do you see my screen now?
I can see the player, but I cannot see any other things. You can.
Yeah, but you see in the player, I don't see where is the chat here. Oh, it's over here. Yeah, so if I do this, is not good because it interacts with. Can you see the screen nicely, or is also the?
It's very clear to me.
But you don't see the Zoom chat, right? It's good. Okay.
It's good. Yeah.
Yeah, I can see it, but it overlaps with the. It overlaps with the screen. That's the problem. Yeah, it's okay. I have a question. Can you see it now? Well, it's still good quality and everything. Yeah.
Yeah, it's very good.
Okay. I'll go like this then. So I exit. I think that's the secret. I exit the full screen mode because it takes a lot of space and yeah. Okay. I'll stop then for a minute now, and I'll mute myself for a minute now. Okay, and be back.
Can you hear me?
Yeah, I can hear you. Can you hear me?
Yeah.
Okay, perfect. Sounds good. I'll mute myself now.
I have a question. Yeah, but maybe for you.
Yeah.
So is the recording starting automatically, or how does it work?
You want to record the whole meeting? Just Could you go to the Zoom window?
Yeah.
And on the very bottom of the Zoom window, there's a record button.
I think it's already recording, Radu. I
Oh,
see.
yeah.
That's why I'm asking. Is automatically recording?
Yeah, it's already on.
Ah, okay. So
yeah, someone started. So you maybe automatically, or you did.
But the point is, when I joined this meeting, I didn't push any start button. I pushed join the meeting. So probably someone else pushed the start button.
Yeah, maybe then it is automated. Yeah, when I joined, it was already recording.
Really? Ah, okay.
Yeah.
Okay. I don't have any problem, but I want to make sure I do the right thing. In fact, there is a tiny sign here. It says recording to the cloud, which I suspect this might be it, right?
Yeah.
Yeah. So, Diana. Yeah, okay, so hopefully this recording goes well because there was a question if these things will be available afterwards. I'm not sure if they meant just the video or the whole thing. So. So Umit.
Yes. Yes.
Yeah, I'm looking at this thing. I'm trying still to figure out. Yeah, should be okay, I think. Yeah.
Yeah, when like at 1 p.m. or 3 p.m. our time.
Yeah.
Everyone will start watching the first video, right?
Yeah.
And then we'll just hang out to see if there's a question.
Yes.
Okay.
We'll answer the questions, all the questions in this box.
Yes.
In the Zoom chat, and then we'll go like to the first two parts one after another, and then break half an hour, and then we'll continue with the third part, and then demos, and then questions and answers extended. So the first questions should be just clarification questions that we can answer through Zoom chat, not complicated.
Yes.
Hello, everyone.
Hi. Kartikeya, can you hear me?
Yes, I can hear you. Can you hear me?
Yes, very well. Yes.
Okay.
Yeah. So glad you could log in. So everything was smooth, huh?
Yeah. Very nice.
Okay, that's good to hear, because it looks pretty complicated at first when you have to think about this VFAIR thing, and is the interface to make it more interactive.
Yeah, they have made it look like a real conference.
Yeah. That's what makes probably things very complicated somehow. I cannot imagine how to handle this, but yeah. All right, good. So yeah, so we'll start at 1 p.m. Promptly, and then keep an eye on the Zoom chat. Can you see it, the Zoom chat and everything?
Yeah.
Okay. All right, so it looks like we're in good shape.
Is Dimitrios joining?
I did not hear about him. I did not hear about him, so Diana may know.
He's not gonna be here.
Okay.
Okay.
So it's just you, Kartik, yeah, from the people who did the heavy lifting.
Yep.
Okay. So, Yebo, I have a question for you, if you know. If you looked at this application, this Hova thing, do you know what those numbers mean? Like, for instance, it says tutorial 86 attending or 200 or whatever. What does it mean?
What numbers are you referring to?
Is under the lecture style tutorial, there is added to my agenda, and in parentheses it says, for instance, for this one, 86 attending. So is this counting everyone who ever opened any of the video clips or what?
You mean on the vFairs or the...
No, under the other one, under the mobile application, the Hova thing.
Probably that's the number of people who added this section to their schedule. I don't know.
I see. Yeah. I don't know either. Yeah, I looked at others and I tried to figure out. It's probably people who just added that on the agenda, not necessarily attending or. Yeah, okay. So I'm wondering, during the break, when we'll take half an hour break, we'll stop the recording, we'll pause the recording or not?
I think it will continue to record. You don't need to do anything. That's my assumption.
That's my assumption too. Okay, just checking.
So Umit moved to Wisconsin-Madison.
Yeah, a week ago, I think.
Congratulations, Umit, on the new position.
Yeah, thank you. This is my first formal engagement from Wisconsin-Madison.
It's your first what?
The formal presentation or formal activity.
Oh, I see. Yeah. So Kartikeya, he went back to the cold part of the country.
Yeah.
After being in 100 plus for a number of years.
Yeah.
Yeah, it's.
So, are you actually moving there now, or do you
just moved. Last week, we also physically moved here.
Physically moved. Okay, cool.
Yeah, he's getting ready for the start of school.
Yeah.
Because pretty much everyone starts around this time. And that's why, yeah. All right. Good afternoon, everybody, and welcome to our short tutorial on Edge AI, Systems Design and Machine Learning for IoT Data Analytics. Before getting into the tutorial, just a couple of clarifications. First, we will play the video clips and as we go along, answer your questions in the chat box. I hope if you have questions, you use the chat box and ask for clarifications. And at the end of each part, we'll have 2-3 minutes time devoted to clarifying other questions before transitioning from one video clip to another. And then at the end, we'll have, in part 4, we'll have a couple of demos, as well as all the presenters and the contributors will participate in a panel that will go into more in-depth questions or clarifications that you may need. And finally, we'll conclude this probably around 4:45 or 5 p.m. this afternoon. So as I said, for the time being, while the video is playing, please ask clarifications questions that can be answered through this chat box. It's kind of limited, but more complicated questions that need in-depth responses will be in the Q&A section at the end. Sounds good? Okay. All these slides are available as a clarification on the tutorial website. So there are links connected to each part of the tutorial. And my understanding is that the entire proceedings will be recorded and be available after the session ends. Without further ado, I'll just start this video and go along with the first part of this presentation. Enjoy. Good afternoon and welcome to our tutorial on Edge AI. This is a joint presentation by Radu Marculescu, Diana Marculescu, and Umit Ogras. With the explosion of big data, it is often forgotten that much of the data nowadays is generated at the edge. Specifically, a major source of data comes from users' endpoint devices, such as smartphones and watches, that are connected to the internet, also known as Internet of Things. This edge of data faces several new challenges related to hardware constraints, privacy issues, and distributed learning. So what systems and machine learning algorithms can we use to generate or exploit data at the edge? Can network science help us solve machine learning problems? Can IoT devices help people who live with some form of disability and many others benefit from health monitoring? These are some of the overarching questions that we'll address in this tutorial. The tutorial is organized in 4 parts. Part 1 will introduce relevant algorithms for IoT and Edge AI, design constraints, and new directions in distributed learning. The second part will discuss new architectures to support the algorithms introduced in Part 1. The third part will discuss characteristics of a few concrete system implementations for distributed edge inference, human activity recognition, guide analysis with IoT devices. Finally, the speakers will conclude the tutorial, show a demo, and answer audience questions. The tutorial is intended for an audience relatively new to the IoT area with interest in edge computing and energy-efficient AI system design. The tutorial assumes basic background in machine learning, network science, and systems design. We will explain the more advanced concepts in machine learning and system optimization in sufficient detail needed to, for the audience to make the presentation self-contained. Here is some basic information about the presenters. I, Radu, will start the presentation with the algorithms section of this tutorial. Then Diana will take over and discuss the architectures part. After a short break, Umit will cover the third part on applications. Finally, after another short break, all of us will answer your questions, show a demo, and conclude the tutorial. Two other major contributors to this material are Kartikeya Bardvaj and Dimitrios Stamoulis, both of them former graduates from the EC department at Carnegie Mellon University. So this concludes the overview part. Let's now get started on part one, namely algorithms. This tutorial targets a new paradigm we call Edge AI, which brings together two important ideas. First is the idea that the network should be at the forefront of IoT design. Second is the need to address three major challenges associated with large-scale deployment of deep learning at the edge. As shown in box A, we have federated learning, a new distributed training paradigm at the intersection of data privacy and network of devices. The idea is to first train the model on each device using local data, then send the model and not the data to some server for a global model update. As shown in box B, data-independent model compression aims at compressing deep networks without using private data sets. This inference problem is at the intersection of hardware constraints and data privacy, which is, for instance, needed in cases like handling medical data. Box C covers communication-aware model compression, a new distributed inference paradigm at the intersection of hardware constraints and network of devices. The idea here is to distribute computation among the IoT devices while limiting the inter-device communication. We note that existing model compression methods like pruning, quantization, knowledge distillation focus on hardware constraints at device level, for instance, latency, memory, or energy, but they do not consider explicitly the network effects, hence the other two challenges, namely privacy and communication-aware design. However, in the second part of this tutorial, Diana will discuss new directions in pruning and quantization that can work synergistically with model compression. Finally, Umit will illustrate these approaches and their use with wearable devices for activity recognition and guide analysis. Taken together, this tutorial will focus on some of the critical research needs and that rely on a network-centric approach to enable edge intelligence and hence fully exploit the true potential of IoT. So the first part that I'm going to discuss covers some basic material in federated learning and illustrates some of the issues that are relevant to IoT design. So federated learning is a recent development in machine learning area with major relevance to edge AI. There exists significant work in this problem space. We focus on federated averaging, FedAvg, which is a standard approach for federated learning. Simply speaking, federated averaging runs several local training epochs on a randomly selected subset from all devices and averages all trained local models to form a new global model. However, since data can be different among different devices, the trained models can often diverge, especially when the data is non-IID or non-identically distributed. FedProx is another approach recently proposed to constrain weight divergence and improve performance for non-IID data. FedProx addresses the weight divergence problem by using new loss function, which constrains local models to stay close to the global model. Getting into more details, federated averaging involves a centralized server and multiple local devices as shown in this figure. These devices can be cell phones, tablets, or personal fitting devices. Initially, the global model is generated by a central server which coordinates the global learning across a network of devices, which each node is a device collecting data and performing some local training. After selecting a subset of devices at random, the server distributes the global model to the selected local devices, and these local devices perform some training, some local training, and this is shown here, a local training epoch E. FW of WK is the cross entropy loss on local data. As a reminder, the cross entropy is a measure from information theory that builds upon entropy and calculates the difference between two probability distributions. The local model is updated with its own data as WK at t+1 using a given learning date and a gradient applied to FW of K. Once the selected local devices perform their local updates, they upload the local models to the central server, as shown in this representation. The server then merges these models by averaging them, and it forms a new global model, concluding the communication, a global communication round in federated learning. We note that while we focus on non-convex neural network objectives, the algorithm we consider here is applicable to any finite sum objectives of this form. From a machine learning perspective, we assume that there are M clients over which data is partitioned, and the server aggregates the local models and forms a new global model as shown in this and in the right-hand side of this figure. To clarify, the objective of federated learning is to minimize the G function, see this equation in the top right corner, where GWK is the local objective, which is typically the loss function of the prediction made with the model parameters W. PK is the ratio between NK and N, where NK represents the number of samples available at device K, while N is the total number of samples. That is, each client locally takes one step of gradient descent in on the current model using its local data, and the server then takes a weighted average of the resulting models. The amount of computation is controlled by three key parameters, namely the fraction of clients that are used to perform computation during each round, E, the number of training phases each client makes over its local data set at each round, and the size of the mini batch available locally for each client updates. Typically, we assume that the full data set is available locally. So now that we clarified the basics of the federated learning, let's focus on the activation divergence phenomenon. This multi-layer CNN model is deployed on each individual device in the federated learning for local training. The activation vectors we select are the output of the last convolutional layer, as shown in this figure. For example, the activation vector can look like this 8x8 matrix. We use yellow to blue to represent the activation values from high to low. The average activity of a filter for a given image is in the validation set is defined as the averaged output of the corresponding output channel fconv. For instance, suppose that a network final convolutional channel has 256 output channels, and the height and the width of the activation map is 8x8 pixels, then to obtain the average activity of filter I, we average the value of its 8x8 output channel activation map. Essentially, we use this average activity metric as a measure of the importance of the filter for a given class of images. That is, the higher the average activity of a filter, the more important that filter is for, say, classifying a set of images. Let's use a simple example. So we have here a frog, and we assume that this image is fed to two devices, device 1 and 2, that implement exact same structure of the convolutional layer as shown before. This image, this frog, will determine the activation vectors at these two devices. These two devices have the same model structure, yet only data they have locally stored can be different. Hence, the weights of the model will be also different. Indeed, since devices 1 and 2 have their own data, the weights will be also different. This is particularly important for cases when we have non-IID data. As a reminder, a collection of random variables is independent and identically distributed IID if each random variable has the same probability distribution as the others and all of them are mutually independent. So non-IID data is when these assumptions do not hold true. Since the weights are different, the activations generated from the same input will be also different. And as shown in this representation, when we pass this image of the frog through these devices, if we focus, for instance, on this corner, we can observe that device 1 has mostly highly active points, while device 2 has mostly low activation points. If we simply average these two models, because of this kind of opposite behaviors, the resulted model will lead to a poor performance in classification. So, as we realize the importance of the activation vector, we can discuss now a new idea, a new approach for mitigating the activation divergence. And this idea consists of reducing the activation divergence for the same classes across multiple devices. So apart for the original loss function FW, we also hope to make this activation vector highlighted in red here similar among local devices. By relying on the principle of maximum entropy, we assume that the prior distribution of the activation vector should be closer to a uniform distribution U, such that it can maximize the entropy and preserve most of the information. As shown in this figure, the final logits of the activation vectors at the input of the last fully connected layer are used in the objective function. KL denotes the Kullback-Leiber divergence and refers to the activation vector U. U is a uniform distribution over the activation vectors. To achieve that, we minimize the KL divergence between the activation vector and the uniform distribution, and this way we actually maximize entropy, hence the name FedMax for this newly proposed approach. Let's see a few experimental results obtained on common data sets like FMNIST, CIFAR10, CIFAR100. The model we use is the multi-layer CNN we just showed. And in our experiments, we simulate 100 devices with 10% of them being involved in training at each communication round. We show two sets of experiments. One has 300 communication rounds with only one local training epoch. The other experiment consists of 600 communication rounds with 5 local training epochs. We use different communication rounds to compare the communication efficiency of various federated learning approaches. So these are the results for the 3,000 communication rounds, and we show here our results for both IID and non-IID cases with 3 different data sets. The blue line is the FedMax line. As we can see, for all 6 plots, the FedMax outperforms the other 2 approaches. In the CIFAR10 non-IID case, FedMax can have more than 5% higher test accuracy compared to the other 2 approaches. As we increase the local training epoch to 5, we need to decrease the communication rounds to 200. And in this case, we still find that FedMax has a better performance than the other 2 approaches, Fed Averaging and FedProx. Besides, in the CIFAR10 non-IID plot, FedMax has more than 6% higher test accuracy compared to the other approaches. This reflects the fact that FedMax can perform better even when it has fewer communication rounds. This means that FedMax is more communication efficient, which is very important for learning on edge devices. Finally, we show the TSNE plot for Fed Averaging and FedMax. As a reminder, TSNE stands for T-distributed stochastic neighbor embedding. It is used for modeling high-dimensional objects by 2- or 3-dimensional points in such a way that similar objects are modeled by nearby points, while dissimilar objects are modeled by distant points with high probability. In this representation, we are embedding the activation vectors in 2 dimensions using TSNE. We show the corresponding accuracy at the bottom and the training epoch at the top corner of these plots. We use different colors to represent different classes. So in this case, we use data from the CIFAR-10 dataset. Hence, we have a total of 10 different colors that correspond to the 10 different classes. In the beginning, all TSNE plots look similar. There is no obvious clustering taking place, which means that the same colors do not necessarily stick together. And implicitly, the test accuracy for both models is low. However, as we reached the 5th epoch, FedMax starts gaining accuracy and forming clusters of the activation vectors. The magenta color here points several points that get together, and this means that the activation vectors of this class become similar across the devices. In contrast, federated averaging has a much slower clustering, and therefore the accuracy is lower. FedMax has more similar clusters as we increase the number of epochs, and hence higher accuracy, as shown here for epoch 14. Finally, FedMax manages to create all 10 clusters for all this CIFAR 10 dataset, but federated averaging has only 7 out of 10 clusters formed by epoch 15. Clearly, this shows that the activation gets closer and closer for FedMax. This helps with the accuracy over the other approach. So to summarize, we highlighted some of the issues that stem from the non-IAD characteristics of data on edge devices, and we proposed FedMax, a new approach that can handle non-IAD data for classification. FedMax can reduce the activation divergence problem that occurs to the non-IAD data in federated learning. It can have a better test accuracy, which is up to more than 10% improvement, and less communication compared to existing approaches. It will be interesting to look deeper into other types of applications and see if FedMax can work for different learning tasks such as language modeling, and to see how it performs with other real type of data. We shift gears now and look into another important problem for IoT, namely model compression. We start with the obvious question, why? Well, most of the model compression literature focuses on inference on a single device. As a result, prior art looks mostly into device type of concerns, and therefore the number of communication-aware techniques for deep learning is significantly limited. One of the basic assumptions made by existing approaches, namely the assumption that the entire model can fit on each IoT device, is actually quite optimistic because many IoT devices are significantly limited in terms of memory. Let's take a simple example. So assume that we have an original model with about 9 million parameters, and through some method we can compress it to about 2 million parameters. If such a model has to be distributed on memory constrained devices, as shown in this figure, where the budget is 500 kilobytes, then the model itself needs to be distributed across multiple devices. This can lead to a heavy intercommunication at each layer of the deep network, as shown in the right-hand side of this figure. Therefore, in the next part of this presentation, we're going to talk about a new paradigm we call NONN, that not only reduces the memory and the computation costs of deep networks, but also minimizes the communication for efficient distributed inference. The literature of model compression is very rich. However, existing approaches for model compression, such as quantization, pruning, knowledge distillation, separable convolutions, are not communication aware and do not address the distributed inference problem. Clearly, pruned models cannot fit on a single IoT device, will need to be distributed across multiple devices, which will lead to heavy intercommunication costs. On the other hand, existing techniques such as SplitNet split the network into disjoint parts using training without any constraints on the individual network partitions. This unconstrained splitting can result in large partitions which may not conform to the memory budgets of individual IoT devices. In contrast, we argue here for compressing such models and accounting for the communication among different modules. This is the essence of the NONN approach that we'll detail next. Existing approaches relevant to the problem at hand come from two different areas. On the left-hand side is knowledge distillation, a powerful model compression technique which consists of two deep networks, namely the teacher, which is the large deep network that we want to compress, and the student, which is a significantly smaller neural network, which is trained to mimic the output of the teacher network. To mimic the teacher, the simplest way is to directly train a student model on a teacher logits, as shown in this figure, the unnormalized outputs of the teacher model before the fully connected layers, instead of training it directly on true labels from the dataset. The basic idea here is that while training the student model using logits instead of direct classification probabilities can transfer more information about the teacher to the student. The second source of inspiration is shown in the right-hand side, and it comes from network science, a new area that turned out to be very beneficial for modeling social networks, epidemics, transportation networks, so on and so forth. However, to the best of our knowledge, we are the first to propose utilizing network science concepts for model compression. The two core ideas from network science that we'll need in our presentation are the concept of node degree and community structure. Node degree of a node refers to the total number of links that are connected to a node in the network. A network can have a scale-free structure if some nodes have many connections, but most nodes have low degree. Such nodes with many connections in a scale-free network act as hubs of information. For instance, nodes A, B, and C in this example can be hubs in this network. On the other hand, the community structure is an important concept for the distributed approach that we want to propose. A community can be defined as a group of nodes for which the number of connections within the group is significantly higher than one would expect to see at random. For instance, in the right-hand side of this figure, we have a community structure highlighted with 3 different colors. And if we would think that this is for a social network data, these communities can denote groups of users that have interest in sports or music or politics. Getting now into more details, Hinton introduced knowledge distillation in 2015, which uses both hard label loss based on the true labels from the data set, as well as the soft label loss, which are based on logits, to train a significantly smaller student model. Let PT and PS be the logits of the teacher and the student, respectively. We can define then the following loss functions: the true label loss, the logit transfer loss, and the total loss, where the H is the standard cross entropy loss and Y denote the true labels. Alpha is a parameter that controls the weight of the hard label loss versus the soft label loss, and tau is a soft targeting parameter called temperature. The temperature parameter in the second term of the total loss equation improves the knowledge transfer from the teacher to the student. Of course, there are other variations of knowledge distillation, such as attention transfer-based loss function, which uses intermediate outputs of the teacher's convolution layers while training the student. Total loss can be calculated as a function of all these parameters that we defined, and it's shown on the left-hand side of this slide. We note that prior techniques use a single student model, and what we discuss and what we propose now is to use a generalization of this approach that uses, instead of a student, a network of students. More specifically, we propose NONN, or Network of Neural Networks, a new framework which allows for memory and communication-aware student architectures obtained from a single powerful teacher model. How does this NONN work? First, we split the teacher's knowledge into independent partitions, as shown in step 1 in this representation. Then, in step 2, we train individual students on teacher's partitions. Since training an individual student to mimic a specific partition of teacher's knowledge is significantly easier than mimicking the entire teacher's knowledge, the NONN approach achieves higher accuracy. At the same time, distributed inference can be then performed by deploying individual student modules on different resource-constrained devices, and these individual student modules will work independently and will communicate only at the fully connected layer. We formulate now the teacher knowledge partitioning problem as shown in this slide. Specifically, we partition the teacher final convolutional layer by looking at the patterns of activation filters as validation images pass through the teacher. We assume for simplicity that all IoT devices are identical and have the same memory budget, so we refer to a homogeneous case for simplicity, but the approach is completely general and works in heterogeneous cases as well. Second, we assume that the memory and the flop budgets are determined by the IoT devices on which the user wants to deploy a given model. So partitioning a teacher's final convolutional layer uncovers quite often a partition P0 which does not contribute to teacher's validation accuracy. Therefore, we should find and remove the largest set of filters P0 since such filters will only transfer noise to the students during distillation. Then the knowledge partitioning problem can be expressed as shown in these equations, where delta val denotes the absolute value of change in validation accuracy due to the removal of the P0 partition. Moreover, the size of partitions of the teacher final convolutional layer should be almost equal in size, such that the resulting student network will nicely fit with the memory budget B-mem, while the computation cost will fit in the budget B-flop. Finally, we have a rule that is used to determine how exactly the partitions are formed. We describe this next. So the key difference between the traditional knowledge distillation proposed by Hinton and this new approach that we propose, NONN, is shown in this figure. NONN relies on network science to partition teachers' final convolutional layer. Specifically, features for various classes are learned at different filters in the CNN. These activation patterns can be then used to create a filter activation network that represents how exactly the teacher knowledge about various classes is organized into filters. For instance, we can have a cat, a dog, truck, car, various such classes. We then partition this network via community detection, and these disjoint partitions of teacher's knowledge are used to train individual student modules. There are many ways in which can be done. We discuss here one possible partitioning strategy we call activation hubs, or AH, which encourages connections between very important and less important filters typically will have a few high importance filters surrounded by many low importance filters, as shown in this representation. So if I and J are two filters with average activities AI and AJ respectively, the Fij link weight for activation hub rule will be high if for a given image either AI is high and AJ is low, or vice versa. Note that if either AI or AJ is close to 0, or when both AI and IJ are very close to each other, this link is not formed. This is because of the term AI minus AJ, which will be close to 0. Therefore, important filters from the same class will be forced by this rule to occupy separate communities. Hence, the knowledge is distributed uniformly across the students. In this example, the color represents filters that activate for a given class, while the size indicates the importance of that filter for a given class. So to sum up, as shown in panel A, the pre-trained teacher model exhibits certain activation patterns for the validation set. As shown in panel B, we use these activation patterns to build a network of filters activity. Community detection is then used on the filter network to partition the teacher knowledge into simpler modules. As shown in panel C, we then train individual students in the NONN to mimic each partition. And finally, as shown in panel D, teacher knowledge can be partitioned in different ways depending on how the filter activation network is built. So we discussed the activation hubs rule AH, but we can also have a co-activation function and so on and so forth. To train the overall NONN, we use the knowledge distillation loss, the equation that we already discussed. But in addition, we propose a new loss function called activation transfer for transferring partitioned knowledge from the teacher to the individual students. The main motivation behind introducing this new activation transfer loss function is that for each partition of the teacher's knowledge, we want to minimize the error between the activation of the teacher filters that belong to a given partition and the activation of the filters in the corresponding student. So we defined the activation transfer loss function as given in this formula, and we can see some sort of normalized mean square error defined for the student and for the teacher. So the total loss is given as shown in the equation at the bottom of this slide, which can be further minimized via stochastic gradient descent. Let's see some results of this approach to see how well they work in practice. And we start with the CIFAR 10 data set. We choose our teacher model as the wide ResNet WRN 40-4, which has close to 9 million parameters. And we choose a baseline student, wide ResNet 16-2, that we use it both with knowledge distillation and attention transfer knowledge distillation. The NONN consists of 2 student modules. We denote this by NONN2S, each being based on a wide ResNet 16-2 structure. We set the number of partitions to 2, and as evident, the knowledge from partitions of only 34 and 46 filters from teacher's F convolutional layer is transferred to student 0 and student 1, respectively, via 1-by-1 convolutions. The rest of 176 out of 256 filters at each final convolutional layer do not contribute to the teacher accuracy, and hence they form the partition P0, which is not used for transferring knowledge to the NONN students. We first trained the teacher on using 90% of the training data set while saving 10% for validation. We also assume that each IoT device has a memory budget of 500 kilobytes. Each student module, therefore, must have less than 500K parameters. We also set the budget of flops to 200 millions, which is close to the baseline flops used by the baseline WRN16-2. As shown in this table, our NONN2S model achieves higher accuracy than the baseline student model. We note that each student in the NONN utilizes actually fewer flops, namely 167 million flops, than the allowed budget of 200 million flops. Moreover, although each student has only 0.3 million parameters, the total number of parameters for the entire network of students, NONN2S, is 0.82 million, which is comparable to the 0.7 millions in the baseline WRN16-2. We also note that after replicating G0, student 0 and student 1 will not communicate with each other until the very final fully convolutional layer. We note that if a device cannot fit more than 500K parameters, prior models such as WRN16-2 will need to be distributed across multiple devices, which will lead to communication at every layer. That is, when distributed, the baseline WRN16-2 will communicate at all 16 layers, as opposed to the NONN2S, which communicates only at the final fully connected layer. We look now at our results obtained for CIFAR 100. Here the teacher is a WRN28-10 model with 36.5 million parameters, and our baseline student is a WRN16-3 model containing 1.5 million parameters as shown in this figure. Therefore, we create a network NONN with an overall number of 1.5 million parameters as shown in this representation. This NONN can be split into two students, where the larger student will have 0.5 million parameters, and also the flops of our larger student will be lower than the WRN16-3 baseline. Again, we observe that the NONN2S model is more accurate than both KD and ATKD baselines, while creating disjoint students that fit the memory budget of 1 megabyte of memory. We note that since our disjoint students fit this budget, other techniques like existing techniques like MODNN can be further used to distribute our model computation on more devices with similar memory constraints in order to reduce the number of flops. Further comparisons with SplitNet, as well as more students, 4, 6, or 8 students, demonstrate the advantages that the NONN approach brings to the table. Finally, we use real hardware to validate our results and demonstrate the effectiveness of the NONN approach for distributed inference. In this experiment, each student is deployed on a different device. So we have, for the 8 student case, 8 different processors, either Raspberry Pi or Odroid, involved in the measurements. So the results for the teacher model deployed on one Raspberry Pi and our NONN2S model deployed on 2 Raspberry Pis, as shown in the top portion of this table. The NONN model clearly outperforms the teacher model network by a very large margin, 13x to 20x improvement in terms of memory, flops, and energy, with only 1% loss in accuracy. Equally important, our experiments nicely agree with the results presented, theoretical results presented earlier. In the similar results we observed for Odroid, and we notice that the NONN energy and flop numbers are reported on a per student basis because we are mostly concerned with per node budgets for memory and flops. We will show a more detailed demo of these experiments at the end of this tutorial. To summarize, we started this part of this tutorial with a fundamental question, namely, can a network science help us design efficient deep learning architectures? The answer is definitely yes. As shown, we can achieve model compression for distributed deep learning inference on a network of edge devices. Network science can be directly used to solve the knowledge partitioning problem, and student architectures selected based on user constraints on memory and flops are very efficient for distributed inference. Our experimental results indeed demonstrate the impact of NONN idea. NONN can result in significantly lower memory, computation, and while resulting in minimal accuracy loss and communication overhead. Accuracy of the NONN is better than or comparable with state-of-the-art distillation techniques. Validation on real hardware demonstrates up to 12x improvement in latency, 14x better energy per node than the teacher, and up to 33x improvements in terms of reducing latency compared to the compression baseline. I included here a set of references, a minimal set of references that can give more details on these ideas presented in the first part of this tutorial. And by consulting these references, we can go even deeper into more and more details to understand the better picture for either federated learning as well as distributed model compression. Finally, we would like to acknowledge useful discussions and help with the experimental part for a few students that helped us at UT Austin or Carnegie Mellon University. This work has been partially funded by DARPA and Amazon Machine Learning Research Program. This concludes the first part of my presentation. Thank you very much, and I'm ready to take a few clarification questions. So, as I said, we have time for... Good afternoon, and welcome to our tutorial on edge. Yeah, as I said, we have maybe a couple of minutes for some clarification questions before going to the second part of this tutorial. We had a few on chat, but if there is anything we can answer now, please do ask. Okay, if not, then we can move to the second part, and then we'll maybe have an in-depth discussion at the end, as I mentioned in the beginning, in the panel style QFA that we'll have. Thank you. So Diana, you can continue.
Okay, so I assume that you would run all the videos, so give me a second to find it. Thank you for attending this part of our tutorial. I'm Diana Marculescu with the University of Texas at Austin. And I'm going to cover the architectures part, as Radu mentioned, how it connects with the algorithms that he described, as well as how do we do system-aware modeling, co-design, as well as efficient inference on the edge. So I'm going to start with a very simple example. I'm sure we have tried this. A typical edge device, your smartwatch or a smartphone. If it's off the network and you ask very simple questions, what is 100 divided by 2, or what is my name, or what is Apple, the company, the answer should be obvious. However, because these devices are not actually able to produce answers without being connected to the network, the answer is not simple. It's, sorry, I'm not able to help you right now. Please try me again in a bit. And the reason for that is that these tests are run in the cloud. They are not run on these edge devices for various reasons. And I'm going to exemplify a few of these reasons, and how do we make it possible such that the answers are readily available on your edge device. As we know, machine learning applications are everywhere, and they do push hardware to its limits. Deep learning is what is used in many of these applications, starting from automotive, IoT, smart home, mobile wearables, virtual, augmented reality, and drones. They all run deep learning to some extent. However, they bring quite a few challenges, and these are the fact that hardware constraints are a key limiting factor. In fact, if you think about how much energy does it take to run object detection on a smartphone, it would actually drain the battery in about an hour. And these are results that have been published quite some time. I'm sure right now with the advent and the, more of the advances that we've seen in machine learning, these would be even more power consuming. On top of this, as you've heard from Radu, there's a lot of edge cloud communication constraints that need to be dealt with, as well as everything that has to be included in terms of privacy. And when we run things on device, we expect certain response time constraints to be satisfied. Otherwise, the quality of service drops. So the question is, can we push the processing of these machine learning, deep learning applications right to the edge? Such that they can be run efficiently on these edge devices in a hardware efficient fashion. The challenge that we have is that designing deep learning models under hardware constraints is hard. And the main reason for that is first that to find a model that satisfies a certain performance or accuracy is hard to begin with. So this is the realm of hyperparameter optimization. This typically starts with identifying what are the deep learning models, model hyperparameters, layers, units, learning rate, everything that we need to perform our task with high classification accuracy or low classification error. So if you want to see this pictorially, we have quite a breadth or diversity of deep learning models with different hyperparameters that vary in their accuracy and classification error. If you add on top of this hardware constraints, the problem becomes even more complicated, especially if you think about one of the components, which is energy consumption. In that case, the spread of the performance of these deep learning models is even higher when you include energy cost. In fact, it's up to 40x for some of these models that actually satisfy a given classification error, but depending on the complexity, they can range up to 40x in terms of their energy cost. How do we find these models? So to give you an example, to identify the best such model, or to parse, say, 12,000 models would require 800 GPUs for 28 days, so a month, which is the equivalent of 62 GPU years. This is quite a significant amount of computation. So the question is, how can we find this combination of models that satisfy energy costs or latency or response time constraints? So this is where system-aware modeling comes into the picture. What we want to do is to bring together what deep learning practitioners and hardware designers do, actually. Deep learning practitioners or machine learners start with a design space. So they start with a design space for the neural network model. And then they have to satisfy certain deep learning objectives like accuracy. On the other hand, hardware designers start with design space for the hardware, the type of hardware components, how they're organized, as well as hardware constraints, real-time constraints, energy costs, things like that, memory footprint. So the question is, can we put these together such that we can characterize machine learning models or neural networks to be able to identify those that satisfy these certain constraints for a given target software hardware platform. And this is what we call neural power. It's a platform, a specific framework that allows us to characterize the power, energy, and latency for deep learning models running on a given hardware platform. And it's a methodology, meaning that you can use it for any type of platform. Neural power is a layer-wise predictive framework that starts with basically a neural network architecture and is able to build automatically and once layer level models and network level models. So once you do this on a given platform, you can use it over and over again for any type of neural network that satisfies a certain characteristics. So the design space for the neural network has to be the same. So for this target software hardware platform, you identify power, runtime, and energy cost with breakdowns, and then the machine learners can provide or get guidance as to which neural networks are best. So how do we build these network level models? Well, they start for energy with layer-wise. So energy is the product of average runtime and average power. And then per layer, it's again power times runtime, but we do this in a layer-wise fashion. So for all the layers from 1 to n, we identify the average power and the average latency. Runtime is the sum of all these end-to-end latency costs, and power is just a weighted average for the average power across all layers. So how do we determine the layer level models? Our layer level models for both runtime and power are determined based on the type of layer. In principle, the way we do it, the latency is a function, a polynomial function of the various features that characterize the different type of layers. So for example, for the convolutional layer, we have kernel size, stride size, padding size, and number of filters as the parameters. For the fully connected layer or the pooling layer, these would be slightly different, but it's a polynomial function. And then with additional terms that actually characterize the type of computation that we do, so the number of multiple accumulate units and things like that. This is the model that we actually fit. So we do model selection to identify which coefficients have to be 0 and what are their values for a given platform. And in a similar fashion, we developed the power model. So we fit this model once for a given platform and for every type of neural network layer. So what are the kinds of results that we can do? This work was actually published around 2 years and a half ago. And at the time, the only way to characterize and compare was to look at prior work, Paleo, that actually was developing similar predictive models, but only for latency, not for power. And if you look at the different types of layers, convolutional, fully connected, and pooling, depending on the model size, neural power is able to achieve much lower root mean square error and root mean square percentage error compared to Paleo. At the same time, if you look at power compared to the actual numbers for both latency and power were obtained using profiling on that given platform. And perhaps absolute accuracy is not as important as it is to look at the breakdown. So sometimes machine learning developers would like to know what is the layer that actually is the bottleneck in this, what consumes most power or it takes most time. So if you look at this, this is an example for VGG16 where we have Paleo neural power and the actual runtime from light brown all the way to black. You can see that neural power is able to actually pretty much agree with the profiling results, whereas Paleo severely underestimates the fully connector 6 layer for VGG16. And this is important because as a designer, you would like to know what do you need to So how do we use these results to look at overall networks and in comparison? For example, VGG16 compared to others. This is runtime and power for several neural networks that we have here. And as you can see, the actual runtime is very close to the overall runtime end-to-end per inference that is reported by neural power. And similar for actual power measured as well as the neural power predicted value. So this is great news because it allows us to do these characterizations once for a given platform. And then if I add another line here for another neural network, I'm able to tell, okay, this will give me end-to-end runtime per inference or this much power. So for this given platform, it's very valuable information. For energy, a similar story. In fact, the accuracy is even better than for power and latency. As you can see, these numbers are very close to each other. And it takes us to an interesting way to characterize these machine learning models by looking at a combined energy efficiency prediction, correct prediction ratio. So we look at the product, a weighted product between the error, the classification error, and the energy per data item classified. So we call this energy precision ratio. And depending on the alpha value, we can give more weight to the accuracy, so we care more about the machine learning performance. If it's lower, then we give equal weight to the energy cost. So not surprisingly, the VGG16, when we care more about error, is the one that is chosen, if you can see here, for EPR. But if we care more about the energy per inference, then AlexNet is a winner, although despite the top 5 error being higher, it is much, much lower in terms of energy per inference. So this is how we can actually compare, sort of do a trade-off analysis between these. So now that we're able to characterize neural networks in terms of their energy or average power consumption, can we actually go forward or move forward towards co-design? And here, the machine learning and system co-design is addressed through neural architecture search. So the question that we wanted to answer earlier, can we identify these networks, these models that are able to give us highest precision accuracy, but at the lowest energy, becomes a question of searching this search space, but identifying which of these are best in terms of energy or latency or runtime. In general, neural architecture search can bring an order of magnitude improvement in energy or latency with minimal loss in accuracy, or can satisfy real-time constraints, but it has to be modified from the original approach for neural architecture search. So this is where something like a single path neural architecture search approach can be useful. So I'm going to detail next how that can be done. In general, device-aware, hardware-aware COMNET design assumes that you do have a device that you want to target a task, for example, speech recognition or object detection or image classification. And then you want to employ in automatic fashion an AutoML or NAS, neural architecture search algorithm, that identifies in a hardware-aware fashion the highest image classification accuracy under a given latency constraint configuration. So the way typically this is done is by having a search space for the neural architecture. For example, the types of convolutional layers, other components, whether it has residual connections and things like that. You also need a way to search in this space. So you need an optimization algorithm, a formulation. And then, of course, you need a way to characterize whether these configurations satisfy constraints. And this is where the models that we described earlier come into the picture. But when you put everything together, this can be very, very costly. As you've seen before, it takes quite a bit of time to search exhaustively the search space. Even done in a smart fashion, this can reach hundreds of GPU hours. So state of the art at this point is around days to do this efficiently. So the question is, can we reduce the search cost of NAS, including these hardware constraints, which makes the problem even more complex, down to a few hours, so we can identify these configurations faster? And the answer to that is yes. So the way we do approach the problem is starting from multipath differentiable NAS, which is existing work. That assumes that your neural network is comprised of layers, and each layer is consisting of multiple types of possibilities or blocks for implementing it. So it could be a conv 3x3, 5x5, or 7x7. And the NAS problem is reduced to selecting or path selection in this supernet. So in this supernet, we represent all possible combinations. And then you have an expensive path level selection in which, for example, if I want to select the conv 5 by 5, then I need to identify whether or which selection in this case, 5 by 5, takes me to the highest accuracy. In differentiable NAS, these selections, so the 0-1 selection or 0-1 program is translated into differentiable formulation such that stochastic gradient descent can be used. So it's interchangeably used for algorithms like that. Such an approach has been used in prior work, and we start from that. But we want to actually remove some of the inefficiencies, because here we need to look at all the weights across all paths. So the search space is not only exponential in the number of selections, but also you have to identify all these possible weights. So this is what leads to a high search time. The way we do it is by looking at a single path approach. The superkernel overlaps all these configurations into a single one. You still have a selection problem. However, the number of parameters is the set of the weights in this particular case for the largest candidate only. And because by doing so, you're able to reduce the search cost by more than 3 orders of magnitude and still achieve state-of-the-art accuracy. So to give you an example, if we're trying to do kernel architecture decisions and we want to make them differentiable, we can represent 3 by 3 conv by the inner weights plus none of the outer shell. Or we can represent the 5 by 5 as both selecting the inner weights plus the outer shell. So it's still a selection problem. However, the inner kernel weights are shared among the 3 by 3 and 5 by 5, and similarly for 7 by 7. So how do we translate this problem, which is still a 0-1 selection problem, to a differentiable formulation? So we basically use group lasso and a trainable kernel threshold variable to represent this in a differentiable fashion. And this becomes one of the objectives in our differentiable search. Similarly, we can do channel architecture decisions differentiable. So for example, for expansion ratio 3 or 6, for the superkernel, for expansion ratio 3, we select the first of our channels and none of the second half. For 6, we would select both the first half and the second half. But if we want to drop completely that layer, then we select none of them. So this selection variable is 0, and this becomes a don't care. And again, the formulation is made differentiable using group lasso and trainable thresholds. Here we have 2 thresholds, one for expansion ratio 3, one for expansion ratio 6. So now we can put everything together. So you can have a search space that includes types of kernel size, conv layers 3 by 3, 5 by 5, expansion ratios, squeeze excite values. We also can have skip ops or not. So when you put everything together, you have a differentiable formulation. And then what you need to do is also put together the cross entropy loss that identifies the best neural network that satisfies a given accuracy or minimizes the error, but at the same time includes a trade-off parameter, in this case runtime. We want to make sure that runtime is included in the optimization such that we identify configurations that satisfy certain runtime constraints. So by doing so, we're able to include not just the accuracy, but also we can include on a platform-specific fashion, in our case it was Pixel 1 phone, the runtime. In this case, because it was a very simple objective runtime or response time, we basically characterized in a lookup table fashion per layer the latency, 5, 7 milliseconds. And our goal was, okay, can we find fast the neural architecture that satisfies, say, an 80 millisecond response time per inference constraint. And of course, because this is a lookup table and selecting one versus the other is still non-differentiable, we use a similar approach with lasso and using this formulation here to make the problem of finding the minimum response time, highest accuracy configuration differentiable. The model that we have developed actually agrees very well with the measured runtime, as you can see here. So we put everything together in our framework. Everything was run, and we were able to compare with existing work. So these are standalone neural architecture search approaches. We also have at the other end, we have manual design. So these are designs that in theory require zero cost because they're not the result of a neural architecture search, but they are the result of engineers fighting these, MobileNet v2, MobileNet v3. And the reason we chose them is because they do are characterized by the same search space. Multipath NAS, where our approach got its inspiration from, is pictured here. So you can see that the cost is pretty high. This is in epochs, and it's at the log scale. So single path NAS actually achieves, compared to these under the same assumption and scenario, the 80 millisecond runtime constraint, but with the highest accuracy, 75.62, top one accuracy. And at the same time, it does so by improving over manual designs, improving all the other automatic approaches, but at the same time, doing it 3 orders of magnitude faster. So if you actually do the computation, it's 5,000 times more efficient in terms of the number of epochs. So it takes tens of epochs as opposed to hundreds or thousands of epochs. So this is good news because we can identify in a hardware-specific fashion these configurations using these models that we pre-developed and using this fast neural architecture search approach. So then what is next to do? So is there anything else that we can do for these models to perform even better on the edge? And the answer is yes. I'm going to concentrate on a couple of them. Like Radu mentioned, I'm going to look at or discuss briefly quantization or lightweight neural network implementations, we call LightNN, as well as pruning. And pictorially, typically, basic or baseline configurations will use floating point or complex arithmetic operations, as well as a lot of the memory, consume a lot of the memory footprint of your edge device. But if you employ this kind of quantized implementations, then you can do away with these ALUs and just do everything with logic, so gates, and then your memory footprint will go down because you don't have to store all these weights and activations. Pruning has a similar impact on storage, as well as response time, as you'll see later. So our claim is that you can actually achieve 2 orders of magnitude better energy with much less area, so they can actually fit on your smartphone or your smartwatch without having to go through the cloud to perform those tasks. So there is a broad spectrum of lightweight neural networks, all the way from full precision that require quite a bit of computation and storage, all the way to lightweight representations. LightNN 2, LightNN 1 actually use only 2 bits of 1 or 1 bit, and I'll explain how that is done. But they do have quite a bit of gap between the kind of cost that they require and their accuracy. So our goal is to fill in this gap and to also fill the gap between full precision and binarized neural networks, where you only use 1 bit that tells you whether it's a plus or minus 1 weight, and push this trade-off curve further towards lower testers, so higher accuracy. So this is where flexible LightNNs come into the picture, as well as binarized neural networks trained with our approach come into the picture. So LightNNs, or lightweight quantized deep neural networks, pretty much replace multipliers with a limited number of shift and adds. By basically identifying which of these powers of 2 will need to be maintained such that accuracy is is maintained as much as possible. So LightNN 1 assumes that the equivalent multiplier is just a shift, so weights are represented only with 1 power of 2, and K equals 2, LightNN 2 assumes that a MAC is replaced by 2 shifts and 1 add. So you have up to 2 powers of 2 in the representation. So a neuron that performs this weighted average becomes just a combination of shifts and adds. In this case, for 2, k equals 2 powers of 2 in each case. It's just 2 shifts and 2 adds, respectively. So it's much cheaper to do it. And the way we do it is by using stochastic rounding to identify which of these 2 powers of 2 need to be used for these weights. In general, the way you train these lieutenants is by modifying the backpropagation algorithm. So in the forward pass, you do this rounding using a stochastic approach, stochastic rounding, that on average guarantees that the accuracy is maintained. And then in the back propagation, when we compute the loss function using the gradients, we revert back to floating point gradients to recover some of the accuracy. And then we update the weights again using floating point and repeat the process until convergence. And by doing so, we're actually able to bridge the gap between existing work like binary connect or binary net. In binary connect and binary net, either all weights or just weights, all weights and activations or just weights are binarized. And as you can see here, this is MNIST and Cipher 10 results. ImageNet set is similar as well. We basically are able to recover the accuracy from the conventional approach. Quite a big gap here. So binary connect, binary net the error is pretty high, but we're able to bridge that by using 1 or 2 powers of 2 in the representation of the weights. Or activations as well. So as you can see, there's quite a bit of room for improvement here, and the cost is actually pretty low. So if you look at how these look like, this is MNIST and this is Cipher 10. Lieutenants fill in this Pareto front, so it's a more continuous, quote unquote, so to speak, because they put more configurations on the Pareto front. Everything that you see as a triangle, it's on the Pareto front. Red is the lieutenant representation, and blue is conventional. And as you can see, red introduces quite a lot more options for designers. So for example, in the case of Cipher 10, we can have 2 orders of magnitude energy reduction, note the log scale for normalized energy here, without losing much or actually at all in accuracy. So we're able to basically reduce the energy of both computation and storage without losing accuracy. And these results are very encouraging because they do translate to ImageNet as well. How can we do further? How can we push this further? We can actually make things flexible. So far we assume that activations or weights are all throughout the network, either using 1 or 2 powers of 2. But what if we allow them to choose during training which of the 2? And this is where the idea of flexible lieutenants or flightenants came into the picture. So in lieutenant 1, filters use only 1 power of 2, so 1/2, 1/4, or minus 2 to the 0, for example. But in lieutenant 2, you can use 2 powers of 2, so 1/2 plus 1/4, and so on and so forth. In Lieutenant, we allow during training for filters to choose which of Lieutenant 1 or Lieutenant 2 can they choose. And this actually turns out to be quite a good option because it allows for a better Pareto front. So this is accuracy as a function of storage required. And as you can see, Lieutenant 2, Lieutenant 1, are here, but then Lieutenant actually allows you to push accuracy to higher levels, which is a little bit counterintuitive. You would expect it to be in between. However, just because you have more flexibility allows you to search the space more efficiently and get better accuracy for a given storage constraint. This is all good news. What else can we do on top of that? For binarized neural networks, which achieve even worse error, training can help resolve some of those issues. The issues that have to do with reduced accuracy for binarized neural networks is that the distributions for the activations and weights actually are marred with degeneration, saturation, and gradient mismatch. So what we need to do is shift these distributions to be centered around the 25th to 75th percentile and enable differentiability. And this is our work that was published last year in CVPR. By doing so, we're actually able to recover quite a bit of accuracy loss. So if you look at prior work in the binarized neural network world, we can recover anywhere from 5 all the way to even more 6 to 7% accuracy. So this is quite encouraging. On top of that, what we can do is try to push this gap further by using pruning. So filter or channel pruning pretty much allows us to simplify the network, if you want, by removing the filters or channels that perhaps are not essential. So we identify those filters, we remove them, we reduce computation and storage. The problem, though, is that accuracy is hurt. So what we need to do typically is to do fine-tuning to recover some of that accuracy for achieving as much as possible the original one. But the model is reduced and is able to run on edge devices. The question, though, is how do we do this? This is a complex, it requires this iterative process of identifying which filters do I prune, do I retune again, and then how do I find the best configuration. So in general, if you look at this pictorial representation of the filters and typically what an accuracy computation flop trade-off curve looks like, depending on the type of device you have, so maybe this is a device, maybe this is another more constrained device, then you would like to prune further. But the idea is that for every single device, you have to redo the work again. And then we need to look at two things. How good is this trade-off curve? This trade-off curve here between this device that maybe is happy with less pruning and this device which requires more pruning. And then how fast do we get this trade-off curve? This trade-off curve can be quite costly. And then if you have to iterate over and over for each type of device, it's going to be very time-consuming. So the idea is, can we build this trade-off curve once, and then depending on the type of device you have, just identify the point of the curve and then use that configuration immediately. So do a lot of work once, but then reuse it every single time with zero cost for every platform. So pruning efficiently is important because in some applications, we do not know a priori what is our platform. And in many applications, we do have changing constraints. For example, in embodied AI applications, both time and destination and the closeness to the target matter. In that case, we might need to adapt the model depending on the target distance, for example. And that takes us to a different latency constraint. So the solution that we found is that instead of iterating continuously, but with pruning algorithms until the target application size latency is satisfied, we perform this work once by providing a set of convnets with various complexities, and you do it once, and then this iterative approach is actually much less costly because you only do it on this curve that you already developed. And the only thing you need to do is evaluate whether it satisfies your constraints. And actually, as we'll see later, once the model size is set to a certain constraint in terms of flop count or other things, you can correlate that quite easily with latency. Our approach is called learning, is Ledger, learning a global ranking. And the idea is that we sort all the filters in importance from low importance to high importance, such that when identifying, say, a target of 80% flop count, then we can easily identify which filters can be pruned away, so the lowest importance filters. For a different target of 30%, we can prune away more. So the idea is you do this learning of this global ranking once, and then you identify this curve that takes you from a flop count to a given filter pruning target. The problem is that, as usual, learning the right ranking is hard. The worst case complexity is exponential. But what we can do is, based on empirical results presented earlier, we use a new ranking metric that performs a layer-wise affine transformation on the L2 norms of filter weights and then maps that into an importance metric. So basically what this means is that if we assume an arbitrary target for the original flop count, we can, based on this global ranking, we can perform this alpha K transformation for all these layers such that they are sorted. So for a given ranking, say I want this, these bottom filters will actually be pruned away for a given say 30% pruning target. So in other words, this transformation allows us to perform this global ranking such that only the lowest, the filters with the lowest importance are pruned away. And by importance, we mean impact in overall accuracy. This alpha K is learned by looking at this objective function here. So this is work that we just published this year in CVPR. And actually results are pretty good because they do recover much of the accuracy lost in all cases. And at the same time, it satisfies the flop constraint. And it does everything once without having to redo this over and over again. So you'll learn this ranking once and you apply it for other types of flop counts. I mentioned the link between flop count and latency. Indeed, if you look at two different platforms, an ARM A57 and Intel i7, as well as two different networks, MobileNet V2 and ResNet 50, there is an almost linear correlation between the flop count and latency. In other words, we can target a given flop count constraint and that translates into a given latency constraint, which is very encouraging because it means you perform this ranking once for a given latency constraint, you can connect it to a flop count constraint, and then that takes you to a certain number or a certain set of filters that have lowest importance to be pruned away. So if you put everything together, what did we accomplish? So we're able to characterize in a hardware efficient fashion machine learning models that typically should run on the edge. We're able to identify those fast in a hardware aware fashion because our approach allows us to do so in a matter of hours. And at the same time, once we identify those models, we can cut the cost even further such that they fit the overall device. So we were able to find the model 3 orders of magnitude faster, but at the same time, we're able to reduce the cost of doing inference by up to 2 orders of magnitude and satisfying runtime constraints. This type of methodology can enable the design of hardware constrained deep learning applications as well as the co-design of edge devices and applications that run on them. So with this, I would like to thank you. I'm looking forward to your questions. The answer to the original question posed to Siri, in this case, if it's off network, would be if I ask what's my name, my smart watch would be able to say, you're Diana, that's what you told me anyway. So having the ability to do this kind of co-design will allow us to have all these applications run truly on edge. These are a few references. If you're interested, they are all available publicly. And they detail they have more details about the work that I presented. And with this, I would like to thank you and acknowledge my collaborators. Much of the work that I presented here was done together with Dimitrios Stamoulis, now with Microsoft, and other students, former students at Carnegie Mellon, as well as collaborators from Carnegie Mellon, Google, and Microsoft. Thank you.
Okay, so it looks like we're on time, we're on schedule, despite some issues that we had. So we have time for a few questions, either for Diana or for my part, before we take a quick break and return with the application side and the demos. So please feel free to ask any of us any clarification question or anything that you'll be curious about. No question? All right, then we'll take a break.
Can I ask a
please.
quick question for
Yes,
Dennis?
please.
I was struggling to find my unmute button. I was just curious whether you think that the architecture design would be similar for natural language applications, or if you think it's specific to image processing.
That's an excellent question. Actually, for natural language processing, obviously the architecture will be very different. The methodology for identifying that architecture might also be different. We haven't looked at that, but it's a great point that it is important to look at ways to do that search. I'm assuming you're talking about the neural architecture search part. One thing I wanted to mention is that there was recent work that showed that natural language processing tasks actually are very energy consuming. So it was work done, I believe, last year, either 2019, around that time frame, where the search cost for identifying these NLP architectures was pretty intense. Actually, I believe orders of magnitude compared to image processing. There is no reason why we wouldn't be able to look at something similar in that space, but we haven't. It's a great point. We would like to.
Thanks.
Okay. Any other question? Actually, we're also interested in that problem space because for distributed inference, and this is a similar problem we have not looked yet. So any other questions from the audience? Okay, then it looks like we can take this break, and as I said, in the third part, we'll continue with the applications, specifically healthcare applications, and then we'll have a couple of demos, one related to the first part that you saw in the NONN approach, and one related to the third part, and then we'll do a panel that will involve all three of us, plus Kartikeya Bharadwaj, who is one of the main contributors to this tutorial. So I think if we stop now, we can get back in about 25 minutes or so to be exactly on the schedule as specified in the KDD.
Radu, are you talking?
Oh yes, I did talk, yeah.
I was able to hear Diana, but not you. Maybe it's just me.
Oh.
I was able to hear Professor Radu.
Oh, okay, good.
Okay.
So, yeah, it looks like strange things go on and off as it happened with my headphones earlier. And I thought everyone is affected by it, but looks like it was just me. So, yeah, so let's take a quick break. As I said, it looks like it's already 25 minutes, and we'll reconvene in 25 minutes to continue our tutorial. I'll just mute myself and stop the video, but we'll come back in 25 minutes. Thank you. So Umit, maybe we can use this break to clarify why are you not hearing me?
Hello?
Hi, Radu. Can you hear me?
Yeah, can you hear me?
Yes, yes, everything is good now.
Okay, I don't know, your video does not have sound or something. Let me try again.
Yeah, I think it happened before. I can, do you want me to play?
I'll do the sharing now. Do you see it? But there is no sound whatsoever. Can you hear anything?
No.
No.
Maybe I can do it because I can hear from my side.
Why is not coming your sound?
I think it happened before with you. I don't know. Let me try if you like. Since we have
Yeah, try it. I stopped sharing.
Okay. Can you enable sharing?
Your co-host.
Not anymore. Since I disconnected and joined, can you make me
Oh,
co-host?
I see. Okay, sorry. Yeah. Can you try?
Still it says I cannot share.
What should I do? You want me to, I make you host?
Yeah, maybe if you make me host.
Yeah, how about this? Can you change now? Can you try now?
Okay, yeah, I can do it. Welcome to the third and final part of our Edge AI tutorial. Can you hear it?
Yes.
Seeing the out. Okay, then maybe we can.
But I cannot hear you very well. That's the problem. I mean, maybe it's just me. It's a very poor quality, very low volume.
Yeah, the volume is very low.
Oh, okay. So did you share the sound too?
It is by default. Mine is sharing the sound by
Double
default.
check.
Yeah. Welcome to the third and final part of our Edge AI tutorial.
It's not better for me, but
and architecture.
Yebo, how is for you?
It's better for me.
Better, okay, but is on par with what we had before, the sound volume?
The sound volume is still lower than before, but it's much better.
Okay, so
Can Diana try since her was also good?
Can you ask me what?
Can Diana share?
Share what?
My video, the part 3 video.
Oh, I don't think she has it. You cannot increase the volume or something?
I don't have the video, but if you share it somehow, I'll try from here.
It is in Dropbox. I shared you. I will send you the link again.
Oh, okay. Yeah, if you can.
It's amazing how these things can appear all of a sudden.
Okay, I'm sending the link.
Okay.
So welcome everyone to the second part of the tutorial, but the third part of the tutorial, so to speak. We'll start momentarily. Just as soon as we figure out this sound issue, we'll start right away. I see it on the screen.
Or am I sharing?
No, it's actually mine, sorry. It's from
Umit, did you send the link? I don't have the link.
I just sent it, yes. Yeah, I sent it.
I have a question. Can we play directly from the website where this is?
Yes, yes, we can also do it. It's a good idea.
Can you try that? Maybe it works better. So, Umit, are you trying that? Or?
Yeah, I tried it, but if I try it, it kicks me out of this meeting. So we cannot do that. So did you receive the link?
Is there any way to start directly playing from?
So I do not have a Dropbox account. I had to create one. It might be the same quality, so I can try this. You have to make me a co-host.
Yeah, you are a co-host. Can you do it now? Yeah, yeah, okay.
Welcome to the third and final.
Oh, it's much better, much better.
AI tutorial.
Okay, so
okay, so we start from the beginning?
Yes, yes. I'll mute myself now, go ahead.
Welcome to the third and final part of our Edge AI tutorial. After seeing the algorithms in part 1 and architectures in part 2, we will move into the applications and energy harvesting devices that can run these applications. The last part of the tutorial consists of 3 topics. We will first overview sensor-rich energy harvesting devices that can implement the algorithms and architectures presented in the first 2 parts. We will also describe 2 energy harvesting solutions that can power these devices. After covering the energy harvesting devices, we will move on to 2 target applications that can run on these devices. The first one is human activity recognition, or HAR, that can be the first step in identifying the movement disorders. And the second one is called M-gate, or mobile gait analysis using wearable devices. We will discuss the challenges and accurate real-time analysis using wearable devices and propose a novel framework. 15% of the world's population lives with a disability. 110 to 190 million people face significant difficulties in functioning. In current health practice, doctors analyze the patient's symptom in clinical visits, which are weeks apart, as shown in the first part of this slide. Therefore, doctors have limited data points and no observability after the patient leaves the clinic. According to the International Parkinson and Movement Disorder Task Force, wearable devices and IoT technology can improve the quality of life of this population. For example, wearable devices can collect data during daily activities and provide feedback to the doctors. Hence, weeks of time between the feedback can actually be complemented with daily data that can help the health professionals provide quicker and faster response to the people with movement disorders. User surveys show that widespread adoption of wearable technology is limited by adaptation and technology challenges that can be analyzed under 3 categories. First, users feel awkward to wear strange-looking devices. Second, many users stop using technology due to maintenance requirements such as charging. Finally, there is a lack of applications with high value. There is a strong interest in mobile technology for health and activity monitoring, as evidenced by smartphone and smartwatch apps. For example, Parkinson's disease biomarker Dream Challenge used iPhones in a study with hundreds of patients. However, they are not appropriate since patients cannot even use them. Moreover, they need to be charged daily, which is not convenient, especially for the target population. Finally, they cannot provide real-time guarantees. Indeed, use of wearable devices in health applications such as Parkinson's disease is increasing rapidly, as shown in this plot. We address the adaptation and technology challenges by a combination of closely related innovations. First, the comfort and user experience can be improved by using physically stretchable or flexible devices, as shown in this figure. By matching to the properties of user skin, they can disappear in clothes or even be used as patches. Second, we provide energy-neutral operation by a combination of energy harvesting and runtime management. This approach dynamically manages the power states of the device to ensure maximum utility under the harvested power budget. Finally, we discuss human activity recognition and gait analysis applications that can be used for patient rehabilitation, fall detection, and physical activity promotion. We prototyped a test board that consists of a TI CC26 series microcontroller with Bluetooth low energy connectivity. It also has an onboard inertial measurement unit, or IMU, with 3-axis accelerometer, 3-axis gyroscope, and 3-axis magnetometer. It also has options to add a stretch and bend angle sensors and a memory card. We manufactured both physically flexible and rigid versions for debugging. We can harvest energy from ambient light and human motion, as we will demonstrate in the 4th part of the tutorial. The average power consumption of the whole device, including sensing, processing, and communication, is around 26 milliwatts, which can be delivered by our energy harvesting techniques. Both hardware and software components are released to public through our Open Health framework. The modular architecture enables new users to implement new applications using our sensor APIs, communication services, and TI's software development environment. Next, we will discuss why we need energy harvesting and how it is different in a wearable setting. First, the bulky batteries are big and prohibitive in wearable settings. Furthermore, flexible batteries have very low capacity, and small form factor limits the battery capacity. Hence, there is a critical need for harvesting ambient energy sources. And at the same time, we need to have an effective management and allocation of the harvested energy in real time to enable self-powered devices that can be utilized for as long as possible using only the harvested energy. But how it is different in a wearable setting? Why can't we use existing energy harvesting techniques as they are? The first answer is bending and stretching changes the shape of the object. As a result, the underlying physics may change and known solutions must be revisited. Next, we provide 2 illustrative examples that describe this need. Photovoltaic cells or PV cells are among the most widely used energy harvesting sources. They have superior outdoor performance compared to other energy harvesting sources. For example, they can have 10 to 100 milliwatts per square centimeters density. Similarly, their indoor performance is competitive with other solutions at 100 microwatts per square centimeters. In addition to this, flexibility offers a great potential for wearable applications. For example, they can be used in wrist watches or anywhere they need to be bent. Suppose that a flexible PV cell is wrapped around the wrist. When it is bent, as shown in this figure, the produced energy decreases significantly. More specifically, the maximum power point reduces by 57% from around 6 milliwatts to 2.6 milliwatts. That is, the conventional models are not applicable anymore. Unfortunately, many maximum power point or MPP tracking algorithms use conventional models of PV cells. Therefore, they may severely overestimate the harvested energy and the operating point. A few recent approaches address bending. For example, a recent work performs IV measurements for a given bending. Then they apply regression analysis to account for the effect of bending. However, this requires a set of measured data at different bending scenarios, elevation angles, and other parameters. More importantly, it cannot explain the reason for this reduction. Our recent work accounts for the bending analytically and provides experimental validation, as we will describe next. When the PV cell is flat, the amount of irradiation received by the PV cell, that is irradiation, is uniform across it. Therefore, the double integral used commonly simplifies to a multiplication. However, when the PV cell is bent, as shown in this figure, the irradiation density is unevenly distributed. For example, the center point has the same irradiation. However, the side close to light has more irradiance, while the side further away from the light source has less. In general, the irradiation changes across the surface. When the PV cell is bent with a radius of curvature r, the length of an infinitesimal cross-section of the arc, dl, is equal to the r multiplied by d theta. We need to take the integration over theta, not the length. Therefore, we also need to find the limit of the integral after this variable change. Hence, the commonly used formulation should be revisited. The expression shown on this slide gives the generalized solution that can replace the conventional one. Of note, the radius of curvature of a flat PV cell is infinity. If we take the limit of our expression as r goes to infinity, we obtain the conventional equation. Hence, we capture the flat PV cell as a special case. We used a commercial flexible PV cell to validate our model. We put the PV cell on a lateral side of a cylinder foam with a given radius of curvature. Then we set the radiation intensity and sweep PV cell output voltage. The experimental measurements show that we can model both the output voltage and generated power with less than 6% accuracy. Hence, these new models can be used both to predict the energy harvesting potential and maximize the generated power. While light energy harvesting is very useful, it's not available in dark. Therefore, it should be also complemented with other modalities. Next, we analyze piezoelectric materials or PZ materials to convert human motion to electrical energy. This modality shows promising harvesting potential and is available on demand. PZ patches generate maximum power when they vibrate at their resonant frequencies, which are usually in the order of hundreds of hertz. Consequently, prior solutions target high-frequency vibrations. However, this requires bulky and complex designs to upconvert the frequencies of slow human motion to the range of those higher frequencies. Some examples of these bulky designs are shown on the slide. In contrast to existing bulky and rigid solutions, we can place small and flexible piezoelectric materials based on microfiber composite directly on human joints as illustrated on this figure. For example, knees and elbows are candidate locations for placing these materials. First, we will present a novel mathematical model that gives the energy harvesting potential at a target joint. Then we will present an experimental setup that validates this model. Through a combination of theoretical and experimental work, we will demonstrate the energy harvesting potential of the knee as the person is moving. The theoretical model consists of two submodels. The first submodel relates the joint bending angle theta to the strain induced in the PZ material. As shown in this drawing, we convert the displacement of the PZ material to the strain, which generates the charge flow. And the equation on this slide shows the generated strain as a function of the periodic walking motion. Then the second submodel converts the induced strain to the voltage generated across the terminals of the PZ patch, as shown in the slide. The generated voltage is a function of the load resistance RL, the PZ capacitance, the capacitance of the PZ material, as well as other design parameters shown on this slide, and the actual strain. We can derive the differential equation shown on this slide that relates the strain to the output voltage. Then we can use the load resistance and this equation to find the harvested energy. The proposed models have to be validated before proving to be useful. Therefore, we designed a mechanical frame that mimics the joint. To achieve reproducible results, a motor generates a periodic motion with a fixed frequency and magnitude, as shown in this video. We performed experiments at 1 Hz and 0.5 Hz and with 60 degrees. This slide compares the harvested power outputs for both PZ patches at all excitation pairs used in the experiments. Hence, there are 8 curves, 1 for each configuration and the PZ material. These plots show that the experimental curves and the model closely follow each other. When all cases are considered, the mean average percentage error of the proposed models is less than 5%. Our results also clearly show that the harvested power increases with the PZ patch. The plots at the top have higher harvested power. They also increase with frequency 0.5 Hz to 1 Hz and angle. Next, we will overview two driver applications that can run on our wearable devices and benefit from the algorithms and architectures presented in the first two parts of the tutorial. We will start with human activity recognition, describe its applications, and an approach for energy efficient offline and online learning. Human activity recognition identifies daily activities such as walking, sitting and driving. Knowing what a patient is doing is the first step to address movement disorder problems. Therefore, human activity recognition can provide a very valuable insight to health professionals. Other applications of HAR include patient rehabilitation, fall detection, and physical activity recognition. Existing approaches for HAR use wearable and smartphones. They enable offline data collection, learning, and inference. However, there is also a strong need to perform online inference to provide real-time feedback to the user. We also need online learning to adapt to new users. At the same time, we want to achieve all this with a low power budget that can be provided using harvested energy. Next, we will analyze an approach that can achieve all these goals. Degrees banding. This slide provides an overview of a new human activity recognition framework. This framework first uses streaming sensor, stretch sensor data to segment the user data into variable length activity windows. For example, the windows can be divided into different steps or periods of time with sitting and standing. Then we use the raw accelerometer and stretch sensor data to generate features for each activity window. This feature set is then fed into an offline classifier design to train the activity classifier. Finally, the classifier is used to make runtime activity classification. Based on user feedback, we can also update the weight of the network using policy gradient algorithms. First, we designed a variety of classifiers using the collected data. For example, SVMs, decision trees, random forest, KNN, and neural networks. Among all these, we will focus on neural networks because they can be easily used for online learning. In this slide, we show a neural network configuration with two fully connected hidden layers with ReLU activation and a fully connected output layer with softmax activation. With this model, the probability of each activity can be found as shown in this slide. Hence, in current practice, classifiers shipped with the devices are trained using only the known datasets. However, user patterns can change with physical condition, age, gender, and demographics. Even for a given user, the activity patterns may change over time as the movement disorder progresses. Therefore, classifiers must adapt to new users and changing behavior of their users. This is a challenging problem since online learning can be computationally expensive. Variable devices do not have large storage area to store training data and the weights. At the same time, processing power and energy requirements may be prohibitive. We have a total. To address these limitations, we define the state as the accelerometer data and the stretch sensor readings within a given activity window. Then the activity probabilities define the policy model. We define the action as the activity performed in each segment. For example, we treat the activity such as walking as the action. Finally, the user provides a reward as a function of the action given by the classifier. For example, if the person is walking and the classifier says walking, then there is a positive reward. In contrast, if the person is walking and the classifiers give a wrong result, the reward is negative. Using these definitions, our objective is to maximize the total reward with respect to the classifier weights. Hence, we start with a trained policy network and then enjoy the feedback from the user, for example, for positive or negative reward, to update the weights online using policy gradient. By updating only the last layer or last few layers of the network, we can both achieve a very good online learning policy and at the same time low processing and energy requirements. of four concepts. The reinforcement learning framework presented in the last slide uses only very simple feedback, which is correct or wrong. If the device allows for more sophisticated feedback, for example, if the device can give the exact label in case of the wrong classifications, then we can actually also use incremental supervised learning. The additional cost here is the complexity of the feedback, but at the same time we can improve the accuracy and convergence time of learning, online learning integrations. All the classification and online learning algorithms are implemented on our prototype. The prototype is attached to a knee sleeve along with a stretch sensor as shown in this figure. To validate the results, we performed studies with 22 users following an IRB protocol and obtained a total of 4,740 activity windows. After labeling each window, we randomly divided the data into training and validation sets, training, validation, and test sets. This data was used for Embedded Systems Week design contest, and it is released to public. In this slide, we show the confusion matrix for all the activities and 18 users. The numbers next to the activity name show the total number of windows with this corresponding activity. First, we observe that the accuracy is greater than 94% for all activities except jump. In jump, we observe a higher error because it shows a higher variation among different users. We also observe a lower accuracy for transitions. For example, when the user transitions from walk to sit or sit to stand. This lower accuracy is acceptable since we can infer transitions looking at the previous and the next activity. Finally, we achieve around 98% accuracy for sit, stand, walk, which are among the most common activities. We also tested our reinforcement and incremental learning frameworks for 4 different users. For each user, we performed policy gradient updates for a total of 100 epochs. We see that there is a consistent improvement in accuracy for all the users. For instance, the initial accuracy for user 9 is 60%. By using online learning, the accuracy increases to over 90% in less than 10 episodes. Similarly, the accuracy for user 6 increases from 74% to 91%. This shows that our HAR algorithm adapts to new users. We also note that incremental learning converges faster as expected. Experiments. As discussed before, energy consumption is an important factor in wearable devices since they run on limited energy budgets. To enable accurate power and energy evaluations, we added test ports to our custom prototype and obtained detailed measurements. This slide shows the execution time, average power, and energy consumption of the leading tasks in the target application. We observe that most of the operations take on average 12 milliwatts or lower. This shows that we have a path towards self-powered devices that can be powered by harvested energy. Moreover, our measurements show that a 200 milliamp battery can provide close to 60-hour continuous operation for our implementation. Finally, we are moving to our final application, which is gate analysis. We will first describe the challenges of accurate real-time analysis using wearable devices. After that, we will introduce a novel mobile gate analysis technique that can provide real-time feedback. Movement disorders are one of the leading causes for functional disability in older adults. More than 10 million people worldwide suffer from movement disorders, while more than 60,000 new patients are diagnosed every year in the United States. Gait function analysis provides valuable insight into a patient's symptoms and rehabilitation. For example, evaluating metrics such as stride length, step length, and gait velocity provide invaluable information. Especially step and stride length are very useful to analyze gait symmetry. However, state-of-the-art gait analysis relies on clinical approaches. Hence, the experiments, which require treadmills and 3D camera systems, are limited to special environments. Gait ride system enables accurate results with a special rug. However, it is very costly, in the order of thousands of dollars. To address this limitation, recent work employs wearable sensors for gait analysis. Most of these studies mount several inertial measurement units, or IMUs, with a 3-axis accelerometer, 3-axis gyroscope, and 3-axis magnetometer to the leg of the user subject and collect data when the person is walking. However, most of the existing approaches need to employ either high cost in the order of few $1,000 or too many sensors, which are not practical. One of the goals to enable energy harvesting devices is achieving similar accuracy to the existing approaches, but at a much lower cost and energy footprint. This technique, called M-Gait, is used for mobile gait analysis. It enables continuous daily monitoring and real-time feedback with 95% accuracy. It does not depend on any clinical environment and experimental infrastructure. It is worn by the user as shown by this figure. It can achieve real-time operation within milliwatt range. Hence, it's a step forward towards devices that can be powered by harvested energy. This work is based on a novel biomechanical model that estimates step and stride lengths starting from first principles. Experimental validation using the implementation on the right and user studies show the accuracy of this model. The pictures at the top illustrate the leg positions during walking. Two critical parameters are the knee and the hip angles. As walking is periodic, both of these angles repeat a full cycle as the person walks. The step and stride lengths can be measured when both feet touches to the ground. Hence, they can be computed using the knee and hip angles, as well as the length of the leg above and below the knee. In short, one can measure the knee and hip angles in real time. Then we can use their values at specific instances, as illustrated in this drawing, to compute the step and stride lengths. To enable accurate step and stride length estimation, we can follow a two-step approach. At design time, we measure the static leg parameters of a target subject. Then we derive the step and stride length as a function of these parameters and angles. For example, the expression for the step length is shown on this slide. At real time, we measure the hip angle using the IMU. Then we measure the knee angle using the bending sensor. By processing these raw measurements, we identify their min and max values to determine the angles at key instances. Finally, we plug them into the biomechanical model. As a result, we can obtain step length, stride length, left to right and right to left timing, as well as the gait velocity. We performed user studies following an official IRB protocol using 7 subjects. The static leg parameters of these subjects, their heights, age, and gender are shown on this slide. During these experiments, users walked over a gate-right rug and on our instrumented pathway. During these experiments, each step and stride length reference is recorded using these systems. Then we found the knee and hip angles using the BandLab and IMU sensors. Finally, the static parameters and angles are used with the biomechanical model to predict the step and stride lengths. We have a total of 3 sets of results. The initial fit was obtained by manually measuring the static parameters of the subjects as shown in the previous slide and plugging them into the equations. This means we simply processed the angle values and then used the pre-measured static parameters in our biomechanical model. Then we further improved the model by first dividing the data into 70% training and 30% test sets. Using the training data, we found the best static parameters using a nonlinear regression. That means instead of using the height and the leg length of these users, we found the best leg length that fits to the data. And finally, we made one step further and then used the same training data to remove systematic offset in sensor readings. The plot on this slide shows the accuracy obtained using all these 3 approaches. The initial fit is within 10% for all users except 2, for which we obtain slightly higher than 15% error. When we apply the first fit, the static parameters are corrected and all the errors are less than 9%. Finally, when we remove the systematic errors in the sensor readings, we observe that we can obtain around 5% modeling error on average. This means we can have very accurate step and stride length measurements with a low cost and practical system. In addition, we can make all these estimates in real time. Hence, we have also the information of how left to right and right to left step takes. By dividing the length into the time, we can also obtain the gate velocity. This means we can use the real-time gate velocity, step length, and stride length to look for outliers or unexpected behavior. For example, this slide shows fixed length walking followed by free walking, where we can see the variations in the step length. And finally, towards the end, we see limping, which shows much higher variations. One can also detect the changes in these parameters and then send a feedback or a notification to the user about this change. Potentially, this type of feedback can avoid falls or improve rehabilitation of patients. In summary, there are interesting algorithmic and architecture innovations that enable edge intelligence as presented in the first 2 parts of this tutorial. These applications can improve the quality of life and in particular assist elderly and people with movement disorders. However, there is a critical need for edge devices and driver applications to fulfill this promise, since comfort and compliance challenges prohibit existing solutions. We presented physically stretchable and flexible wearable devices. We also presented energy harvesting solutions from light and human motion to power these devices. Finally, we discussed 2 high-impact applications: human activity recognition and gait analysis. The references used in these presentations can be provided upon request.
Okay, thank you, Umit. Looks like we're right on time now. If there are any quick questions for Umit now, we can address them now. Otherwise, we move to the two demos, each of them about 4 minutes long. Okay, if there are no...
there is one question on the Zoom chat.
Oh,
the question is, how do you foresee edge intelligence interacting with the control systems in critical applications? I think this is a very nice, very important question. One problem here we have is energy harvesting or limited energy. So whenever we don't have enough battery power, or if we run out of any energy resources, these type of applications that we have considered so far will have to be paused. But if it's a critical application, this is probably not an desired solution. So I think there should be, as of now, they are not applicable to safety critical applications. If you want to make them applicable, there should be some mechanism that will enable graceful degradation in the services. So before, for example, the battery will run out, there should be some backup that will at least ensure that the results out of these systems cannot be trusted. But without them, I think they are not ready for safety critical applications.
There is one more, Umit, I think still on the chat.
Yeah, this is also a very good question. So the question is, for the RL method, for the human activity recognition, do you assume that the true label is immediately available? So for the reinforcement learning solution, we don't assume that the true label is available. Instead, we assume that the user will tell whether the output was correct or wrong. For example, while we are, let's say, biking, the system says we are walking. So here, the feedback we will be getting is wrong instead of bike. So by just making use of false or true, correct or wrong decisions, the reinforcement learning approach tries to improve. There is another one which we call incremental learning. In that one, we are showing that if somehow the feedback is more sophisticated, and if the feedback gives the true label, then the approach works and it converges faster. So if we can have a better feedback system that will enable the user to give the true label, it will improve the accuracy and the convergence. But we don't have to have that.
Okay, great. So I think we can try now to go to the demos. And the first one is a demo presented by Kartikeya Bhartbaj, who is the contributor to this tutorial. And it relates to the first part of this tutorial, specifically to the NONN distributed learning part. So I'm going to try to play it, see if sound and everything else goes well. Just 1 second, because okay, so I'll let it go now. Hopefully everyone will see and hear well. So
let's look at the demo for network of neural networks. So this is our setup over here. What we see over here is basically a bunch of Raspberry Pi devices. So specifically, we have 8 Raspberry Pi devices that are connected to each other via point-to-point wired connection with the switch over here. And we also consider like other devices, like these are MC1 devices, which have ARM big little architecture. And all of these devices, like we can see, are connected point-to-point to each other. So to measure the power for Raspberry Pi, we use this power meter, this silver power meter over here, right? So this is actually connected to a desktop computer where we can in real time measure what voltage, current, and energy numbers are, power numbers are, like we see over here, right? So, and for MC1s, the power can be measured with these power meters that are connected to the MC1s. So I'm going to show a quick demo of how things execute on this network of devices. So the idea here is that we compress the model into disjoint parts, and each of these small devices is executing a disjoint part. So here basically we see a lot of terminals, and for example, this one is one of the Raspberry Pis. So we have 8 total Raspberry Pis, and then the fully connected layer is executing locally on this laptop, which is x86. And so I'm just going to run through this. This is CIFAR 10 dataset, and like we can see over here, it starts executing a lot of images, and at the same time, so this is the homogeneous case. We have 8 separate students executing on started executing, the current value increased significantly, and it basically indicates that the Raspberry Pis are executing the NONN models, the individual student models. So here we actually measure like how much time it takes for transmission, how much time it takes for computation, and how much overall time it takes per inference. And after this is done, we basically have measurements for all 3 things: accuracy, latency, as well as energy consumption per device. So I think we can stop here now, and we can basically see, like here you have computation time, which is this calculation time over here, and as we can see, this is a millisecond or something like that for NONN model. Okay, so let's look at the demo for network of.
Okay, and now will be the second demo, which will relate to the part 3 of our tutorial.
Hi everybody, I'm Umit Tuncel. Welcome to our presentation on variable piezoelectric energy harvesting using human motion. The following video highlights our motivation.
What if you didn't need a battery to track your activity? The combined benefits of low power consumption and edge processing allow these devices to be powered through energy harvesting. Flexible light and motion energy harvesters can replace batteries, hence making the design less bulky and removing the recharge requirements. Come join us. Focus on your health, not the batteries.
I will start with the major innovations and contributions of this work. Now, first, we focus on energy harvesting from low-frequency, large-bending human motion using flexible piezoelectric transducers. In contrast to our approach, existing approaches typically use high-frequency vibration as the motion, and they use brittle and inflexible piezoelectric materials. Second, we develop a mathematical model that relates the large joint bending motion to generated electrical energy. Now, this model is useful to predict the energy harvesting potential from a wide array of different motions, such as walking, running, or cycling. There is no modeling study in the literature that target large bending human joint motions. Third, we design and fabricate an experimental setup to demonstrate the energy harvesting potential from the same low-frequency, large bending human motion. Through this setup, we collect important experimental data from different MFC piezoelectric patches and validate our mathematical model. Most existing work placed the piezoelectric elements directly on human subjects, which do not yield repeatable and reliable results. Also, previous work do not combine the experiments and models together. I'll introduce the setup in more detail now. First, we have the frame that mimics the joint. And on this frame, we place the flexible piezoelectric element and clamp it from one end. The other end is free and is coupled to the frame with the help of a transparent cover that is placed on the upper leg. The piezoelectric element slides under this cover. The frame is actuated by a dynamic cell AX12A servo motor, and the motor is controlled through an open CM motor controller. The two terminals of the patch is terminated by a variable resistance box. And finally, we record the generated voltage with an NI DAC at 1 kilosamples per second. Here's a short clip of the system in action. Here we charge 100 microfarads. The following results have been obtained from the MFC 8528 piezoelectric module. Starting with the voltage, we see that it is 10 volts peak to peak. We can also see that the output waveform is distorted and is no longer a pure sinusoid. Next, we illustrate the generated power for different bending motions. For the power results, I'll just focus on the 60-degree 1 Hz motion, as it is the closest among these four to human walking in the interest of time. With this motion, the system can generate up to 10 microwatts of power. In summary, we presented an experimental exploration of energy harvesting from joint bending. To conclude the presentation, our model predicts that we can harvest 7.8 microjoules per step when walking. This is sufficient to power many low-power designs. As a reference, 10,000 steps per day over a month is equivalent to 0.5 milliamp hour battery. For more details, please refer to our 20-minute presentation on the conference webpage. Thank you for listening. Hi, everybody. I'm Umit Tuncel.
Okay, thank you. So that was the the second demo. Right now, we're at the end of the material that we wanted to present, so we can have a in-depth discussion Q&A style in order to go over different parts or relate one to another to make everything clear, or whatever it's relevant for the audience to clarify at this point in time. So you don't need to put questions in the box, in the chat box. You could directly ask them on Zoom. So yeah, please go ahead and ask whatever questions you find relevant at this point. So isn't there any question for any part of the tutorial? Anything that you would like to have clarified, or? If you do, please unmute yourself and then ask the question.
There is a question in the chat window, Radu.
Yeah, I saw it just now. Yes. So the question is, in terms of architectures, what are the main bottlenecks currently? It's more memory or computational power when we think about this edge AI application. So I would like everyone to chime in. So in my view is both. In other words, memory is limited because of these devices have small footprints typically, and they have memory limited. Computational power is also limited, but I would also like to add to this the communication aspect, which makes this inter-device communication very expensive. So that should be accounted is a major cost as we move from, say, a centralized approach to a decentralized approach where communication between devices will be necessary to implement these various tasks distributed. So I think this is a major thing, and it has even a more a higher impact, more significant impact when we think about applications like 3D object detection or this kind of thing. So for now, most of the stuff that we discussed, at least in the first part, was centered on image classification and this kind of applications. But as we move to more complex applications like 3D object detection, I think that becomes even more important.
Hello, this is Hussein, a PhD student from York University at Canada, Toronto. I have two questions. One general question about the future direction in general, what will be the future direction in the area. And the second question is a bit more specific about the first part about the federated learning that you're talking about selecting the M devices to do the local training. So you said that those devices are selected in random. Is it any other possible way that we can select those devices for the better local training?
Yeah, that's a very good question. And the short answer is yes. And there is already ongoing work in this direction because there are other important factors that come into the picture. For instance, some devices may not respond. Some of them may be very low on power and they cannot participate in this pooling stage. The results that I presented there are, let's say, the first iteration where we looked at this random approach. So it assumed that all the devices are available and able to join, because some of them may be having enough power, but maybe the connection is not good, and therefore they are not able to connect to receive the model from the server. So this is a very interesting direction. And in fact, the most important I think application when it comes to this will be to connect that with the NAS part, the network architecture search part, that will be able to define models that are appropriate to different types of devices that we have there. Yeah. And that was your second question?
Yeah. The first question was pretty general about the future direction.
Yeah, I'm biased. I personally believe that this has a lot of potential, and in fact, it will get a lot more attention that it has now, meaning machine learning for IoT or AI or edge AI for this kind of applications, simply because people will want more and more to see these AI applications be run locally and privately, so to speak, in order to avoid sharing everything with the cloud and with this. So in general, I think it will be 3 levels, more or less, where things will happen. One will be related, it's the obvious area dominated by Google and Amazon and the like, will be the data centers and whatever. There will be a second layer, which will be Apple and the like with these phones and these devices, and will be the third layer, which will be dominated by, I'm using an example, ARM, which will have this kind of low power, low memory processors that will be spread all over the place. And technologically speaking, there will be a lot of progress from this kind of devices that are like the electronic tattoos and things, or which will be embedded in everyday's object, either invisibly or with little impact. And that will boost this area. And I think it will have tremendous growth over the next 5 years or so.
Yeah, I agree with Professor Radu's comments here. And I would like to chime in about future directions that concern like the co-design between deep learning algorithms and processor architectures that accelerate the execution of these deep networks. So I'm pretty sure there is a lot of ongoing work in that direction. Professor Diana suggested a few directions in that space, and yeah, so it's like it's a very complex problem because we need to take into account what deep networks we are running right now, as well as what kind of networks we will run in future. And that becomes a complex problem on its own because there are, as you know, the deep learning as a field, it's growing very, very fast. And building deep learning models typically requires, resources like GPUs and stuff. But it's mostly simulation at the end of the day when you're building algorithms. But building hardware is a harder task and it's much more slow. So we need to anticipate what's gonna be very important in the next year or so and build relevant hardware that can accelerate those new deep networks on the edge.
So if I can chime in a little bit, so I think this can go beyond deep learning, and like in our previous discussion, we were talking about beyond image or video processing, and I think Umit's talk alluded to some of that, right? Because it's not just images or video that we're processing, it could be natural language, it could be a combination thereof, especially in VR, AR applications, you have multimodal data sets that you have to consider. So, so we have to think beyond the current set of applications we're considering. So not just neural networks or deep learning, but think of all the machine learning applications and the backbone, the algorithmic backbone for them. That's one thing on one hand, and like Radu mentioned, the platforms will be different. So everything, I mean, right now, when we talk about edge, we're talking about the things that are obvious to us as edge devices, but technology will take us to other unlimited possibilities. And with relation to the previous question that Sarah asked, what is more important, memory or computational power? Well, it'll depend on the application. So just like in neural networks, it depends on the type of layer that you consider. Convolutional layers or fully connected layers, they're very different in terms of the memory or compute intensive footprint, right? So it really depends what kind of AI you're talking about, or what kind of machine learning task you're talking about. But definitely, if we're talking about classic compute model, we do have memory as a main wall that we have to pass, that nothing has changed there. So there's a lot of things that could happen here. You could have progress or evolution in the platform space. You can have a lot of changes in the algorithmic space and the machine learning application space, as well as in the technology and computing model space. So when you put all these converging, I think there's a lot of things that can be achieved. We basically look at a very tiny place in this huge cross product of possibilities here. So, so I think this is very exciting. It's hard to say which one is going to be the winning one, but definitely applications like what health applications or personal body monitoring applications, those are definitely of interest, especially with the current kind of crisis that the society faces.
Yeah, I want to add, I completely agree with what you said. I want to add one more thing here. In fact, two. One is indeed this kind of applications which are beyond classifying cats and dogs and these things, where the machine learning will definitely shine. Because ultimately classifying cats and dogs and whatever is just the static part of the story, and this will fade away pretty soon once we have this kind of technologies available. But the second one I want to notice, I don't know how relevant is this, but to me was very relevant. I noticed recently in the past 3-4 months, a lot of change in the discussion while listening to various podcasts. There are various podcasts on AI, on data science, on all kinds of topics related to this problem space. And I was shocked to see a lot of change in the tone toward what I can call energy aware machine learning type of thing. And for instance, people who are trained as classical physicists or neuro scientists made this kind of transition to say, oh, it's not important to do this or to do that, to mimic the nervous system or to mimic the visual system or whatever in the human body, but rather to have this energy constraint in mind, front and center in designing these new machine learning applications. And this is coming, for instance, from Qualcomm, from one of the lead people in designing the future of Qualcomm research, which pointed out this. And he said, particularly for everything else that concerns Qualcomm in terms of applications like 5G, 6G, 20G, I don't know how many Gs will be there. They said this is going to be crucial. So in other words, people who never did anything in this problem space, actually talking concretely about hardware constraints, co-design. I heard the word co-design between hardware and machine learning models from a classical physicist, and energy as a main limitation in this kind of applications. So I think everyone is clear about the potential of this area as we move to next technological phases, but also the impact of this kind of things that will have to be considered, which are primarily coming from the limitations of the hardware, whether or not it's memory, whether or not is bandwidth to communicate. Essentially, this kind of hardware constraints will be playing a more and more important role, I think. Is there any other question or any other comment on this or anything else?
Hi. Yeah, can you maybe shed some light on also the role of maybe time series models? This, as you said, there are like audio and video, and I think also time series will have a role, or it can be used along with edge AI, especially maybe in industrial IoT, for example, or
yeah, absolutely. That's a great point. Not only this, I'm going to bring it, or I'm trying to bring it closer to the stuff that we discussed in the tutorial. For instance, thinking of the kind of applications that Umit presented in the third part, where you have all these sensors everywhere to sort of help either elderly or people with disabilities. All these things will have time as a fundamental component, as a component that will be continuously sensed. So it will be X, Y, Z coordinates as well as timestamps. So this will generate huge time series that can be used to make super interesting inferences and try to make predictions about various situations, all the way from someone falling, all the way to I'm sorry, someone maybe having COVID. If this one of these things monitors the cough, for instance, and you can make by analyzing the time series, you can make distinction between a cough that comes from instance from a long-term user of tobacco compared to someone who changes the cough because of the initial stages of COVID. So time series analysis is crucial for analyzing various patterns of movement when we talk about human disorders related to movement, but also to speech, to the heart rate, because this is another thing that can be monitored and can be used in conjunction with the breathing to classify or to detect certain conditions, essentially anomalies. So what I'm trying to say here, I'm trying to say that these two components that will come together, in other words, multimodal sensing on one hand, as well as the analytics on the other hand, which are going to be heavily dominated, in my view, by time series analysis, are going to bring enormous benefits to the society, I think.
Yeah, and
maybe I can give an example for the time series. In human activity recognition and gait analysis applications covered in part 3, there are two main sets of sensors. One of them is collecting 3-axis accelerometer, and that is used to measure the knee angle, for example, or the hip angle, sorry. It is used to measure the hip angle. And another sensor measures the bending and stretch to find the knee angle. And we saw that the Fourier analysis of the stretch sensor gives very nice insight about the walking pattern. So we can find actually the dominant frequency to find the speed of like how fast the person is walking. And using these angles, we can get a lot of information about the step and stride length. And then we can identify anomalies. Like for example, we can say the walking pattern of the person started changing, or the steps are not symmetric. And this type of insight can lead to, for example, fall detection. So time series has been very important, like time series from multiple sources, multiple sensors. And I think they will be even more important with new sensing technologies.
So I also have one more question, which is not too far from the previous question. Do we consider the data on the edge device to be static data or non-stationary data that is changing over the time? Let's say the distribution is changing over the time. So if it's not, if it is a non-stationary data, so then what would be the challenges that arise from that and how we can address them?
For the human activity and gait analysis, there is no assumption on the stationary properties of the data. Like one application area, for example, is rehabilitation. Like suppose a person has one sort of movement disorder or recovering from an injury. And we think that the walking pattern of the person will change in time. So we don't assume that it is stationary. As the person recovers, or in some cases as the disease progresses, as it becomes more severe, then there will be a change. But these changes are very slow. Like for example, over seconds or over minutes, our walking patterns will not change. So with that, we haven't seen like big complications because they are not stationary, but at the same time they are very slowly changing compared to the dynamic activities.
Absolutely. I want to add to this. I'm bringing it back to the issue I mentioned a minute ago on the heart rate monitoring. That's heavily non-stationary. And in fact, it's throughout the life, it's non-stationary, and even so it changes. Yeah. Even is more than non-stationary. So typically the non-stationarity and these kind of things are characterized by self-similarity. And for heart rate, it's known to be not only non-self-similar or self-similar, I don't know how to say it, but also it changes to have multiple coefficients over the lifetime of an individual. And I'm talking both about healthy individuals and people with heart problems. So it changes, and because of that, dealing with this kind of signals, for instance, when you think about interaction maybe between sensors and some pacemakers, has to account for this kind of non-stationarity. So to kind of sum up this set of ideas, I would say heterogeneity in data and heterogeneity in devices, which was brought up a little bit earlier, are two probably of the main challenges of making these edge devices, edge AI, a reality.
Okay. Okay, thank you.
Sure. Looks like the discussion is quite interesting now. So if there are any other few points, any other comments, that would be great, because that will make it more interesting.
What about industrial IoT or edge applications? I think there we could afford maybe a little more expensive architectures compared to like the other applications for human detection, activity detection and stuff like that. Or what do you think?
By industrial applications, you mean things like, I don't know, say airplanes manufacturing or this kind of thing?
Yeah, manufacturing.
These kind of things?
Yes.
3D printing, or I forgot what other angles here. So this is what you mean?
Yeah, I'm asking about this, like what current applications, or is the research direction more going towards industrial applications, or the other applications with human activity and health, as you mentioned?
I didn't look at, that's a very good point. I didn't look at any money statistics or whatever, but with this revolution that I see now happening in the manufacturing, you read left and right all kind of things that change, all kind of fundamental changes in the flow due to these nanotechnologies and extremely precise sensing. I do imagine that it's a significant effort in terms of an interest in that problem space too.
Yeah, I think a lot of industrial applications can have the IoT plus machine learning angle, because, for example, I think I heard somewhere about leakage detection in pipelines and stuff with sensors. So you can have these sensors that are connected to each other, and they're sensing some amount of flow of I don't know, like some kind of fuel or whatever. And then if you start to notice some kind of patterns on the time series of all the water that's flowing through the pipelines and these kind of water networks, for example, then yeah, we can totally, if we bring machine learning to those sensors, then maybe we can better detect those kind of faults, for example. And similar things can happen in manufacturing pipelines for different kind of applications and stuff. Right now, a lot of other applications are actually going towards image, video, speech, text, which are pretty obvious because we use them day to day with phones, smart devices, smart TVs, smart, you name it, like it's all over the place.
I have two quick comments on this. I realized only now, one that is growing like crazy these days is the smart agriculture, okay? And there is all combination between analytics or machine learning and this kind of AI techniques and IoT type of devices. So there is this big and long-term concern of food becoming a problem at planetary scale. So there are already either through NSF or to other consortiums, there are efforts to support this kind of research and to make the agriculture smarter. So I think this is an example where it's clearly, if you look at those call for proposals or the kind of projects that they find, IoT is front and center everywhere. And the second one is this direction with the personalized robotics. Okay, there is a lot of interest into this area lately, and I'm sure that these kind of robots that will try to, I don't know, to a certain degree mimic humans or whatever, will benefit to this kind of edge infrastructure in order to be able to augment their capability to solve more complex tasks or to be better at them, starting with hospitals all the way to other applications directly in the factory or in movement of goods and anything else. So I think, yeah, these are probably two examples where there is already a lot of interest and a lot of growth projected for the next decade or so. Yeah.
Thank you for your answers.
Mm-hmm. Sure, you're welcome. So I'm not sure if there are people from who's from industry, but it will be very interesting to hear the angle from that side of the world in terms of perceived growth and perceived interest into this IoT plus AI type of problems. So
or anybody in traditional KDD spaces who can comment on what else can use, you know, computationally efficient execution on edge devices, and if something, yeah, just as a discussion, I think that would be very helpful.
Yeah, in fact, you bring a very interesting point, because I was looking yesterday on this mobile application that has the conference, and I listed my expertise into certain, areas, and I was looking at how the interest varies and how it gets distributed across multiple things, like ranging from applied machine learning to deep learning, to federated learning, to imitation learning, to network architecture search, to whatever, and to IoT. And given the audience that is typical for KDD, the IoT is still underrepresented in my view, because by a factor of 10 at least. So for instance, even if I'm new to this conference, to say, I found people matching interest in, for instance, in deep learning 150, in IoT 5, right? And I think the part of the reason is actually why we proposed this tutorial in the first place, to kind of bridge these communities, because the stuff that we discussed today is at the intersection of machine learning, say, networks and systems. And systems, by systems I mean system design. And I think it's still to be established and to grow in significance inside KDD, because traditionally the mainstream KDD audience is mostly focused on algorithmic problems or more theoretical problems, as opposed to, say, looking also at the interaction with the systems that have any hardware constraints or any kind of limitations like that need to be considered, like memory or communication or power, whatever. So it's hopefully will be a growing interest into this type of problems. Okay, so any other comment or any other question for us? Okay, if not, then I would like to remind you again that the slides and the video will be available. The slides are already available in there is a link that was sent around in the chat. I do believe a couple of times already. So you could see that and eventually contact us for more information or for any idea that you have. Second, I would like to thank everyone for the interest in our tutorial and for the patience to stay through this almost 4 hours, it's 3.5 hours. And feel free to reach to any of us and to continue the discussion even beyond the slot that was allocated to this tutorial today. Thank you very much. And to my co-presenters and contributors to the tutorial. Thank you.
Thank you. Thank you.
I have a question now. Is there any need to stop me or the recording, or it will stop automatically? Probably
Once you exit, it will stop, I believe.
I see. Okay. All right. Thank you very much again, and wish you all the best with the research, and enjoy the rest of the conference. Thank you.
Thank you. Thanks. Bye.